So we've got homework that's due
on the 17th.
Yeah, a week from today. Now, Monday there's no class. So
Online lecture?
what's that? No, it's a day off, so we'll just call it a day off, I think.
You can watch your YouTube video while you
So, all right, so here's the first one here. And I don't have my pen with me. Okay, so let's. All right, so we've got a couple of these problems here. Why don't we have a look? Here's the first one. So what's the first thing you do on these?
Well, are you going to add both of the internal forces? Or the like ones, like at B, where you add the 24?
Yeah, I guess first thing you always do is make a free body diagram. I mean, that's step number one. So, now I don't mess around too much on these things. I want to, so I'll put the free body diagram right on the sketch itself. I won't redo the whole thing. I'll just do that and that. So that's 2200, and this is 4800 here, right? All right, so we'll start there. Okay, so now next thing I do here is I want to know all the forces acting on it. So to accomplish that, I'll take a sum of fx and set that equal to 0. And then I'll just add everything up. So that's 4200 minus 4800 minus 2200. And then I'm going to have a reaction there, RD. So as I have it drawn up there, that would be plus. I've got a sign error. Yeah, that's plus right there. All right. So based on that, I can get RD, and that comes out to be 1600 newtons. Okay. All right, y'all good with that? Now I find that reaction so that I'll know all the forces acting on the object. That's why I'm doing that. Okay. Okay, now, I'll probably want to get the areas of these cross sections. So for instance, this one right here is 0.00283 square meters. I just stay in meters when I'm doing metric stuff. Okay. All right. Now, if I want to find the normal stress in AB, what's the next thing that I do here? Yeah. So I need a free body diagram. I'll cut anywhere between A and B. Okay. And when I do that, I'm going to get, a free body diagram. Now I could use, when I take a free body diagram, I use one whole side or the other. My goal here is to find the internal forces. So there's the load anywhere between A and B. Now I could have used the other side as well. It'll be more work because there's more stuff on the right, but I could use that as well. Okay. All right, so I could use either free body diagram. Doesn't matter which one. If I'm in a hurry, I'll use the one to the left because it's faster, but I don't have to. Okay. All right, and then I want to solve for the internal force is what I want to do. You okay with that? Okay. Now notice in both cases I've assumed tension, but on the left-hand free body diagram, tension pulls to the right, but on the right-handed free body diagram, tension pulls to the left. But I'm making the same assumption on both sides. Okay. Good with that? And then I'll just do sum of fx equals 0. So on this one, it's negative 4,200 plus the load in AB. So when I solve for the load in AB, it comes out to be 4,200, and it's a positive answer. So what the positive answer means is that my assumption was correct. It was tension. Okay? So a positive answer when you're doing statics means your assumption was correct. I can do the same thing over here. And I can solve for the load in AB. And once again, I'll get a positive 4,200 when I run those numbers. Now this time, you know, on this free body diagram, the positive PAB was to the right, so it does indeed act to the right, so it's in tension. On this free body diagram, I assumed it went to the left, so it went into my equation as a negative. I got a positive answer for that assumption, so that means my assumption was correct. It does act to the left, okay? So that's the meaning of that stuff. That's, you know, that's what that's coming out to be, all right? So I've got PAB on both sides now, 4,200. You okay with that? So just, you know, and just cut through what you want to know, but you got to take one entire side or the other. You can't just pull something out of the middle. That's not correct. You can't do that. You got to take one whole side of the object or the other. And then once you've got that, you can solve for the stress. Okay. This is P over A. So that would be 4,200 newtons divided by the area, 0.00283 meters squared. And that comes out to be 1.49 times 10 to the 6. All right, so what I do with this stuff is I keep everything in newtons and everything in meters. And then I just convert that into units when I'm done. So I ended up with when I use newtons and meters squared there, I get 1.49 times 10 to the 6 newtons per meter squared. So that's megapascals. And it's positive, you know, it's tension, okay? So, you okay with that? We got any questions on that bit?
So if you're choosing positive or negative for your forces, is negative is always pulling out from like the foundation, and then positive is the reaction?
No, there's different sign conventions going on here. So what I'm doing on the top is I'm doing statics, okay?
Right.
And so what's happening here is I'm assuming tension, but here, you know, or let's see, right here, I assume tension, it's pulling. But that goes to the, well, I'm sorry, it's right there. That's acting to the left, okay? So that goes into the statics equation as a negative because it goes to the left. For PAB, I'm assuming it acts to the right on this free body diagram, so it goes into the equation to the right. When I solved, I got a positive answer, and that means yes, it does go to the right. On this free body diagram, I'm still assuming tension. It's pulling, but it's pulling to the left. So when I set up my statics equation, that's a negative because it's going to the left. Then when I get my answer is positive, and positive means yes, it does go to the left. It's tension. So there's a few sign conventions floating around in here. You got to use them at the appropriate time.
Right.
You know?
I mean, I guess it's like you could even just ignore the positive and you can put like left, right, or put arrows in your numbers when you're writing.
You could, yeah. I mean, right positive, left negative is, you know, it's just arbitrary.
Right.
That's just somebody decided that long ago. But the important thing here is what goes into the equation depends on what direction you assume it acts. This acts to the left, so it went as a negative. What comes out of the equation tells you whether that assumption is correct or not. They mean different things depending on whether you're going into the equation or coming out of it. Okay.
So just to clarify what you just said, very simply, you make an assumption. If it's positive, you made the right assumption. If it's negative, towards the end of the problem,
Yeah.
PAB, if it's negative 4,200, then you know that you made the wrong assumption.
Yeah.
Then you make the correction.
Yeah, and the correction is just turning it around. That's all the correction is. Yeah. Yeah. Right. Okay. All right. We're good with that. Okay. And they're all like this. This is the approach you take on all of them. I mean, but it's an important thing to learn. This is part of the first little thing to learn in strengths. Is this stuff. Okay. Good. So that's us due Wednesday. Okay.
Was it just 103? I think there's another one.
It's 103 also.
102 and 103.
Thank you.
Yeah, it's 103 is quite similar though. It's a similar problem. 103 there isn't like a blank sheet for it. It's on page 1.
Okay. Thank you.
Mhm. All right, now let's have a look here at how we test materials. All right. So what we do is we take these metal, they're called coupons. They're just samples of metal that are milled down to standard shapes. They're sometimes rectangular. If you got a small tensile testing machine, if you got a really big, strong one, you'll make them cylindrical and bigger. So we used to have a tensile testing machine here on campus. I don't think we do anymore. I think it was sold off at the metals companies here, Ormet and places like that. Wachang, they've got these. Okay, so I'm on page 125. I'm not quite to that spot yet, but that's where we're going. Page 125. So what we want to know about these materials. So we take these, they're called coupons, okay, and we put them in a tensile testing machine. And we tear them apart and we measure them as we tear them apart. Okay. So the tensile testing machine looks like that. It's got big jaws on it, and it has hydraulics. And what it does is it just takes that piece of steel in this case, and it just tears it apart. And it moves usually at a constant rate. So it pulls both directions on the sample. They put a measuring device on there called an extensometer. And then they measure the lengthening of the sample as it's being torn apart. Okay. And then you graph up the results is what you do. Okay. So there are the samples, and you test the samples until they fracture. usually. And so that's what they look like after they break. And then you record the data. Okay, the data looks something like that. And this is what you've got on page 125 is a picture of that I'm showing you here, okay? All right, so this kind of gets you an idea graphically of what occurs with that sample as it's being torn apart. So what happens here, initially, there's a linear portion of the graph. Now, usually it's not quite as linear as I'm showing you here, but it is pretty much a linear, and they also say generally an elastic portion of the graph. So the line goes straight up. So as you pull harder on the material, it lengthens more, which really isn't rocket science, is there? But there's kind of a directly proportional relationship. So what we're plotting up here is the stress, which is the load over the area, divided by the strain, which is the deformation over the original length. That's the general thing you plot. So the x-axis is the strain, which kind of tells you how much it's elongating, and the y-axis is the stress, how hard you're pulling. Now the elongation is divided by the original length, and how hard you're pulling is divided by the original cross-sectional area. But so we get strain for the x-axis, stress for the y. So strain is a backwards 3, it's epsilon. Greek letter epsilon, that became our letter E. That's strain. And the y-axis is sigma, which became our letter S eventually, I think. Okay. All right, so the first part of the graph is generally linear. There's a straight relationship between how hard you pull and how much the sample elongates. And think of the atomic bonds there as just being stretched out, like springs. Okay. So there's what's called a proportional limit at the top of that graph. That's the limit of this linear relationship. The slope of this linear portion of the graph is delta sigma, the change in stress, divided by delta epsilon, the change in strain. That's the modulus of elasticity, E. Okay? Now, being as we're starting at 0, 0, delta sigma over delta epsilon is just sigma over epsilon. Okay? So the stress over the strain for that linear portion of the graph is a recognized slope. It's called either Young's modulus or the modulus of elasticity. Okay, either one. And that should be down below there. I think I call that out. Okay. Okay.
What was the other one called? You said Young's modulus?
Yeah.
Or?
Young's modulus or the modulus of elasticity, one or the other.
Oh, okay.
Okay, great. Yeah, Young was the scientist who came up with this. So, if you want to be a famous scientist, the 15, 16, 1700s was the time to be around, because you could just determine that it was a straight linear relationship, and you get something named after you. Nowadays, you got to do a lot more complicated stuff these days. Okay. Yeah, right. Then you might get a footnote in Wikipedia or something, but that's probably about all you're going to get out of that, right? Okay, now you can keep pulling, and that relationship will start to flatten out a little bit typically. Okay? Now you can go a little bit beyond the proportional limit, and you'll still be within what's called the elastic limit. Now within the elastic limit, if you release the load, if you take the load off, the material will return to its original length. It'll just go right back down that line and go back to right where it was. If you go beyond the elastic limit, it won't. If you go beyond the elastic limit, the material will unload and have a permanent set in it. You'll stretch it a little bit. You'll deform those atomic bonds, and they won't be able to get back to where they were. That's on the next page there. Okay.
So like a spring?
Yeah, that's been stretched too far. It won't come back. Yeah.
Now, wouldn't anything beyond the elastic limit be considered like the plastic or something?
Yeah, they call it the plastic region. So there's all different names they use for these things. It's a little inconsistent from what I've seen.
I was just curious if I remember.
Yeah, I think that's right. That's the plastic region. Okay.
What region or what part is that?
Well, we'll get to that just in a minute. How's that? Okay. So elastic limit is the next point. Okay, the next point is the yield point. Now, what's happening here is you start to stretch these bonds out. There's a point when you just start ripping them apart. You've stretched them too far. It's like you've totally deformed these springs, and all of a sudden the material will just stretch out like taffy, you know. If you pull on it, like you ever blow on a balloon where it's kind of hard, and then all of a sudden, bang, it just pops right up. You know that feeling? That's called yielding. This is that plastic area. So for very little extra stress, you'll get quite a lot of elongation. That's what happens next. It'll just kind of, it really resists very hard, then all of a sudden it'll just give up and it'll really stretch out. Yeah.
Is that considered a failure?
Well, failure kind of depends on what you want to call it. Generally speaking, yeah, for engineering design, you definitely don't want to go there. Yeah. For a few reasons. One is you can't predict what it's going to do, because for a very small extra stress, it'll change length quite a bit. And the other is it's just in such a state of chaos inside the material, you can't really be sure what's going to happen, and you definitely don't want to go there. Yeah, question, Josh?
But if you're like strain hardening a material, then you would want to like carefully adjust to that
right.
point.
And then come back and go out and come back. Yeah, right.
Yeah, I was about to say that.
Yeah.
Like cylinder head bolts, you have to stretch it.
Yeah. Yeah, there is something called strain hardening where you actually go beyond that limit, then release. Yeah, and you create a new material, basically, new material properties. Okay. Okay, now what's happening now is you've busted those bonds and everything's kind of given up and everything's stretching, and there's all these fracture lines in the atomic. It's actually a crystal. It's not a real clean crystal like a diamond or something, but metals make crystals. They have certain shapes that they bond into. Okay, and so you stretch that crystal out. Now you've got these fracture lines and they start moving around and they start running into each other. And then the material hardens up a second time. Okay, so there's an initial kind of rise in the graph, then a flat yield. The second time, all these fracture lines are kind of interfering with each other now, and that material can't stretch out so easy anymore. So that's the second hardening phase. And eventually then it will fail, okay? It'll break. So that's kind of a classic graph for a material. Now they're all a little different. An actual graph would have a much longer yield. I couldn't, an actual graph would really look something like that, okay? I just couldn't put that on a piece of paper and make it look like something. So, I shortened up the yield phase quite a bit on this graph because, all right. Not every material has a nice linear phase. They're not quite as linear as I'm showing there. Some materials, like cast iron, are not very ductile. They don't stretch much, so they just kind of go up and go bang and break. There's all different parts of material, different properties. But that's the basic idea and the basic areas of the graph. Now, the other thing here is after the strain hardening, the material will do something called necking, where it'll get quite a bit thinner in one location where it's going to fail. Now, that makes calculating this graph pretty difficult because you've got a changing cross-sectional area, which is used to calculate the stress. Now, if you actually calculate that changing cross-sectional area when the material necks, this line will keep going up until failure. But that's very hard to do and not really worth the effort because normally we don't go to that region of the graph in our engineering design. So what they use here to calculate is they use the original cross-sectional area or the nominal cross-sectional area, the original one. If that's the case, if they use that number, what happens is the stress appears to tail off a little bit. If you use the original cross-sectional area, which is larger than the true cross-sectional area as the material necks. Okay. Okay, so an actual graph, it would keep going up until failure, but the true plotted graphs where they use the nominal original cross-sectional area, they actually drop off at the end a little bit, okay?
Are you just doing that for exaggeration, or is it just a little bit that it drops?
It depends on the material. And like I said, there's lots of things that get variable here depending on the material, yeah.
Because for the cross, like per the amount of force that you're
Yeah.
applying, there's less material
Yeah,
to
yeah.
hold it.
Right.
So it would have to get much, much stronger to continue getting stronger at that point.
Well, what's going on, the Y value is the force divided by the area. If you keep the original large cross-sectional area, that makes the stress appear to be less than it truly is. Because the stress is going up not because the force is increasing so much, but because that cross-sectional area starts to get smaller as the material necks. But, it isn't really that useful of a number to track, so they don't bother with it too much. Okay.
It's not designed to evaluate that
Yeah,
situation, really.
and and there's not much use to evaluate it. It's hard to do, and it's not that useful, so they don't bother with it. Okay. Other questions on this or anything? We good on that? All right. Okay, we went over the idea of elastic limit. So if you go beyond the elastic limit, when you unload the material, it will not return to its original length. It'll have in there what's called permanent set. Okay, okay. Strain hardening is when you load something beyond its elastic limit. Okay, and you can play around with materials. With metals, you can do things to them to get the properties you want out of them. Some materials you might want to be ductile, and stretchy, but that tends to be a softer material. Some materials you might want to be hard, but that's a more brittle material. Okay, so you have to kind of compromise a little bit with what you might want. The classic example is old swords. You want a sword to have the core of it to be ductile. So it's flexible. It'll take a blow and still not break. But you want the edge, you want a hard material on the edge. So they develop ways of laminating them to get a hard material on the edge and have the core still be a flexible steel. What kind of steel do you suppose you want for structures? Do you want something hard and brittle or ductile? You want ductile, yeah. You don't want like a cast iron for a structure. You use a ductile iron. The reason is two things. One is it'll deform before it fails. So you're going to have some time to look at it and go, something is going horribly wrong here. Let's get out of this building sort of thing. And the other thing is you don't want something to shatter. You want it to, which cast iron will do. You can take a sledgehammer to a cast iron stove and crack it. You can break it, but you can't do that to an I-beam. Okay. So what you want then is you want the material to elongate and deform, and that way it absorbs energy. It's a much safer failure mode. So you want a ductile steel for a beam. They're usually mild ductile steels. Okay.
Is it just assumed that they're all going to be ductile, or?
No, they're made that way. They're made out of a type of a steel, ASTM 30. I can't remember. There's a certain designation for most structural steels. 36, yeah. Okay. Okay. Now another thing we've got is the yield point. I'm showing you a graph that has a very definite yield point, but there's actually a method to find it. And the method is you start at 0.002 strain, okay, which is 0.2%. 0.002 is 0.2%. So you start at a strain of 0.002. You draw a line parallel to the rising limit of the graph, and you intersect it with your stress strain curve. And wherever that intersects, that officially is the yield stress. Okay? And this is done because the yield point can be hard to identify. And you can't, so rather than having different people identifying different yield points, they came up with a standard method. So they picked a good average value of strain that they could use to mark the yield point for a wide variety of materials. And then they just draw a parallel line up from that strain of 0.002 and intersect. And by definition, that's kind of the official way of finding the yield stress with what's called the 0.2% offset method. Okay.
So if that initial line's not linear, it's like how would they get parallel if it was just
I'm not sure on that one, I don't know. Yeah. So the question was if that original rising line isn't perfectly straight, which often they're not, how do you get the parallel? I think you kind of do the best fit kind of thing. There's even like a calculus term for that, right? Mean value theorem or something like that. You know what I mean? Get that average slope and use it, I would imagine, but I don't know. Okay. And keep in mind, actual data is not this pretty. It doesn't look, I made this graph nice and clean so you can see the different things, but real data is not that clean by any stretch. But also keep in mind that even today, if you're designing a structure, you use about a 40% safety factor, okay? Something like that. So, if you think the thing has to bear 1,000 pounds, you design it so it can handle 1,400 pounds, 1,400. So we throw a lot of safety factors into structural type work for these very reasons, We just want to be darn sure that, one, we can't perfectly model all this stuff, and two, we want to be just darn sure it doesn't break, So why don't we take a look at a video here that'll show one of these tests. So, where's this thing? Here it is.
You can just hyperlink it.
Yeah, I guess I could. For some reason I didn't on that one, I'm not sure. Yeah, I guess I just could have. All right, this is just a little video from Britain, I think.
The Tensile Test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Ludus Effect. After a certain strain, known as the Ludus strain, the force increases again. The material opposes an increasing force against the imposed elongation. Its strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the...
Okay, so that gets you some idea, of what's going on there. Here's just a 30-second video. That's brass there, I think. And they'll just pull that apart. You'll see it necking. See those two little dots in there? They've pounded those in. That's called the gauge length. That's a standard distance apart, so it could be measured after failure. Okay. See the light down there? There we go. See the necking? Bang.
Seems like a clean break even with brass.
Yeah, it's pretty much, yeah.
Is there a reason why it...
Hello, today's screencast is all about tensile test definitions.
Probably,
So,
the
when
reason
learning
that it would
about engineering, there's a whole bunch of
there is
new
probably,
concepts that you
if you
probably
get
haven't heard
into
of in, say, any of your science classes.
the atomic properties, there's just more fractures in there, more crystal imperfections. It just happens to be the weakest spot. It'd be different every time you ran the test.
Would it, okay, okay.
Oh, the same material will act different spots?
Yeah, sure. It just depends on what, those crystals, they're not perfect, so.
That makes sense though, like, but not every single one is gonna be exactly the same, so
No.
the neck is gonna occur.
Yeah, wherever it happens to be weakest, that's where that would occur.
Goodbye.
Yeah, pretty much. But those machines are quite strong. I mean, they're just taking steel and tearing it apart, basically.
Yeah, seriously.
So, I mean, I guess maybe this is a little bit too much detail, but how does the machine not like jump and snap?
Yeah, the machine doesn't jump and snap because the machines generally are set to elongate at a constant rate. Not to exert a constant force, but to elongate at a constant rate, which is one of the reasons that force jumps around a little bit. Okay.
Usually hydraulically, actually.
Yeah.
They have like a flow control valve. So even though you're hammering on it, even after it breaks, it can only flow so much.
Which is that controlled rate that you were just talking about?
Yeah, right. So yeah, that'd be a way, you just got a certain flow rate in of hydraulic fluid to move it a certain amount. Okay.
I've actually fixed one of the machines for what call
Oh, really? Okay.
the welding lab. You had to pass a test for you to like weld the metal back together. And
Oh,
it's got to be stretched out by X a distance before it breaks, and if it breaks, you fail the test.
Mhm.
Better do it.
Well, it's stronger than the original material.
Yeah, and actually, yeah, the machine filter got plugged up because it was in a certain state. So, yeah, not just.
Oh, man.
Yeah, it was all like hydraulic. It was like
Okay.
a 220 volt
Oh, yeah.
phase. It was pretty,
I don't know.
pretty heavy duty.
sure. Yeah. Here's HDPE, high density polyethylene. Okay, there's the tensing machine, the tensile tester. Okay, so upper and lower grips, load cell, crosshead up top. Then the extensometer is right black. That's the extensometer right there. So that measures the length. Okay. Now this test will go a lot quicker. It's just plastic. Okay, and you can see this is very, very ductile compared to metal. But it'll do the same sort of thing. It'll eventually thin out and neck somewhere, and then it'll fail.
Seems like it stretches much more.
Yeah.
It's more ductile.
Yeah, right. They've got organic bonds as opposed to like a crystalline kind of bond. Yeah, so that, that obviously,
It's like pulling bubble.
yeah, it is, yeah. Different bonds.
Just because the machine is pulling it and it looks like it's stretching doesn't necessarily mean the material itself is that soft. Like you can't just, if
Oh,
you
no,
take it
no,
out of
no.
the machine, you won't be able to just bend it easily.
Oh, no,
It's
no,
still
no.
holds, right?
Yeah, sure. I mean, yeah, that's it's just a, very strong machine. It's hydraulically driven. Yeah, I can.
Well, you would have undergone so much strain hardening at that point. That it would. Have you ever like tried to break a paper clip? You get to that point, you're like,
Yeah.
you can almost not do it. That's strain hardening. So that would be the result.
I don't even understand because I always break my paper clips.
So depends.
All right, here's a concrete cylinder. Now they do compression tests on concrete because concrete you don't put it in tension, you compress it. Whenever it. Yeah. Or no, it's the other way around.
Other way around.
Yeah. But if you need tensile strength out of concrete, you put big rebar in it, mild steel rebar. Okay. Now this will fail a little bit more dramatically, I think, because it's brittle. See, concrete isn't ductile; it's brittle. And it's got different ways it fails, and it kind of depends on how cured it is, how long it's allowed to set and dry. But that's just a few Oh, slow motion, yeah.
They had the rebar to make it more ductile.
What's that?
When they add rebar to steel column or concrete columns like that, does it make it more ductile?
Yeah, well, the steel is more ductile. It doesn't make the concrete more ductile, but it is, and it gives a framework for everything to hang on to. But it also gives it tensile strength too. So it does a few things. It can give it, at 20 window strength is not as strong. Concrete has to cure. 28 days is the standard of getting full strength or close to full strength. To reach full strength, it takes forever actually to reach full strength. But 28 days was the old standard. Now in these days with all these different admixtures and stuff, I don't really know, but pure concrete in 28 days was kind of the standard of getting it close to its ultimate strength.
Well, and as you said, isn't the ultimate strength actually forever away? Like
Yes.
it'll continuously.
Yeah, it's an exponential curve. Vertical orientation, 2.2 inches per minute. Brown egg this time. We got go with brown eggs, they're stronger. Okay. Yeah, they are. They're better for you.
You don't get the double yolk?
Okay. Let me take a break here. I've gotten all worked up watching that. So we'll take a little break here.
Non-organic.